Hello students, I hope you guys are doing all right. So welcome again to our next class in energy systems and environment. And today is probably going to be our sixth class and we'll look at electricity. Okay. It is such a general term, but actually there's a lot of things happening behind the scene where directly connected to how we use our energy, okay, and how that energy is actually generated, transmitted, and then distributed to us, right? So in this class, we are going to learn about first the generation and transmission processes, okay? And then we'll also describe voltage and electric usage unit, okay? And lastly, we'll top it off with discussion on the price and tariff of electricity in Malaysia. Okay? So when we are talking about electricity, okay, we cannot help but go back to the basics, right? Because I want you guys to understand as well how electricity is actually being produced. Okay? So if we look back, we have to zoom in to the very, very small elements and atoms. Okay, so if you look at elements, elements is the simplest form of matter, okay, and it's made of atoms. Okay? And atoms is like the smallest piece of an element, and it contains all the properties of that element. Okay? So in atoms, there are a few different components. Okay, there's the nucleus, which is the center, and that center actually contains protons and neutrons, right? You can refer to the figure here. Okay. So protons is the positively charged atomic particles, and then you have neutrons, which is uncharged. Then apart from that, you also have electrons. So electrons is negatively charged particles, okay? And then you also have electrons where it's at the outermost ring, it's called valence electron, okay? So basically, if you look at the atoms, okay, and you look at your table of elements, right? And this is very familiar to us. Okay, this is a table of elements. If you look at the atomic number, okay, the one that is there, 1, 3, 4, so that is actually equals the number of protons in the nucleus, right? And that is actually the identity of that element. Okay, so this one is actually a Bohr atomic model. Okay? And from the table of elements. So for example, this is nitrogen, okay? And this is a representative of nitrogen atom. Okay? And basically, you will have 7. If you calculate here, 1, 2, 3, 4, 5, 6, 7. So that's actually 7 protons and 7 electrons. Okay? So FYI, just to put it out there, so Bohr atomic model is actually the model itself is a very simplified version. Okay, because if you look further into that, there's actually an updated one where atom doesn't actually look like this. Okay, where your electron is actually in forms of clouds, right? But for our discussion, this would suffice, I would say, okay, because it gives you a general understanding about this. Okay, so keep this in mind because this is going to help you understand in the next few slides, right? So basic atom structure is this. Then, the number of electrons just now, it has its own orbits, okay? And you can have even 7 layers, okay? That is possible with, the atoms, which are larger, which are heavier. Okay, you can have 7 orbit numbers. Okay, but usually we can look at that and look here. So in orbit number 1, which is the innermost, okay, it only contains 2. Okay, and in orbit number 2, it only contains 8. So that is the maximum. So if we have something, this is uranium, it's 92, right? So you're gonna have something complex like this. But imagine with hydrogen, for example, yeah, you only have 2. Okay, so only 1 ring. Okay, and that follows according to what atom you're looking at. Okay, but always remember, orbits closest to the nucleus will fill up first. Okay, so it's always going to be from innermost to outermost. Okay, but the one at the outermost, where if you remember just now, we say valence electrons. Okay, so the valence orbit, it never has more than 8 electrons. Okay, now electron flow. So of course, if you wanna, this will relate to how electricity is produced. Okay, so just bear with me. So you remember back just now, you have to look at how atom is stabilized. Okay, so atoms actually prefers to have their valence ring either filled, so it's full, or totally empty of electrons. Okay, because that is the most stable and least reactive form, right? And at the same time, an electron from one orbit can knock out an electron from another orbit. So that's how electrons can actually move, okay, from one orbit to another, and from one atom to the other atom. Okay, so when an atom loses an electron, we always want to seek another electron to fill the vacancy. Okay, so if you pull all of this information together, right, we think back about electricity. Electricity is generally a flow of electrons. Okay, so I highlighted this in our previous lecture, okay, especially during the fuel cell, okay, how, fuel cell and PV, basically how the electrons will move, and that will generate, the electric current. Okay. So basically, electricity is created as electrons collide and transfer from atom to atom. Okay, so imagine you have a wire. Okay, how does electricity move from one end to another? It's because there's an electron flow between the atoms from this end to that end. So imagine if you have just one tiny wire, which is only one atom wide. Okay, it's not entirely impossible, but just bear with me. So if you have something like that, okay, imagine this is your wire and your atom is structured in such a way. Okay, so you have electron which moves. Okay, it transfers from this atom to the next. Okay, displaces another atom here, and that atom will go to the next one, and the next one, and the next one. Okay, so that flow, it creates electricity. Okay, that is basically how electrons can move from one point to another. Okay, and how electricity is electricity is generated from one point to another. Okay, so just now when I say the preference of an atom, so it's either they want it, the valence orbit needs to be completely filled or empty, right? So if you look at that, like copper, it has 29. Okay, the atomic number is 29, and you have sulfur, the number is 16. Okay, so what is the relevance of knowing that, right? So if you have copper here, okay, and you only have one electron at the valence orbit, okay, and you compare that to sulfur, okay, which has 6 electrons at the outermost orbit. Okay, remember, it's either 0 or 8. So what is the relevance? What is important here? Okay, actually, this is why we have conductors, okay, and insulators, right? So if you have something like this, something like copper, okay, the electron wants to move out, okay, from the atom. So that makes it a conductor because the electron is easy to move in or out, okay. Whereas for sulfur, because you have 6 here, okay, it's much harder for sulfur to lose all 6 electrons rather than, you know, getting 2 in, okay, because they want to fill it up. So that makes it an insulator, right? Because it only accepts electron, but it doesn't release that, right? So that's what makes a material either a conductor or an insulator. So it basically relates back to this, right? The components of an atom. Right. So okay, for me, so basically to separate between conductors and insulators. Sorry, I have a typo there. So it should be insulators, right? So conductors, electrons flow easily between atoms, whereas for insulators, it's very difficult. Okay, and you have the outer orbit has 1 to 3 valence electrons. That makes it a conductor. Okay, whereas if you have 5 to 8 valence electrons, that makes it an insulator. And usually, if we're talking about electricity, okay, these two works in tandem, right? There's always going to be both because if you look at wires, right, there's always going to be conductors where, you know, it transfers the electron, and then you have your insulation to make sure that that electron doesn't move elsewhere rather than the direction of the wire. Okay. Now, electrical circuit, okay, is actually a system of conductors and components forming a continuous path for electrical current to travel. Okay. So always keep in mind, you need a complete system. Okay, it must be connected. All of this must be connected. Okay, and of course, there's the significant keywords. You have voltage, you have current, you have resistance, right? So if you look here, right, basically, you have a switch, you have the load here, which is in the form of bulb. You have your wire, and you have your power source, which is the battery. Okay, if it's connected, okay, the light bulb will emit light. Okay, whereas if you switch it off, okay, like this, you're not going to get any light here. Okay, because why? Because there must be a complete pathway for the electrons to move. Okay, because remember back just now, what is electricity? It's a flow of electrons. So you must have a complete flow or circuit, right? And this is very significant later on, which I will highlight. Okay, but just look at that in this perspective, in this small, very simple circuit. Okay, needs to have all of this, right? So we'll look at a little bit about the significant keywords here, okay, and how it relates actually to what's happening. Okay, so if you have, so usually when people are talking about electricity, okay, one of the easiest way to convey that is by referencing a water system like this. So you have a tank, a water tank, okay, you have your pipe, and you have your faucet. Okay, so basically your tank is battery or power source. Okay, and you have your pipe, which is a wiring, and you have your switch here in the form of faucet. right? So what is voltage? Voltage is actually the force that causes current to flow, and it's measured in volts. Okay, so it's actually the pressure. So imagine when you switch, okay, or rather this is faucet. So you switch it on or off, okay, the pressure is always going to be there, right? So it's, for example, when it is off, okay, when it's off, so this is not connected, you have your pressure here, which is pushing against the pipe, the tank, and the faucet. Okay, whereas when you turn it on, okay, the pressure will push the water or the current through the system, right? So voltage is always going to be there. Okay. And then you have current. Current is actually the flow of electric charge, and you measure that in amperes. Okay. So if you Google this, okay, if you look at current, amperes is actually the number of electrons per second. Okay, so remember always, if you have something per second or per time, it's going to be a flow, something that is moving. So in this situation, it's the electron. Okay, so flow of electric charge. So basically, when you turn the switch off, there is no flow. Okay, meaning there is no current. Okay, that's why if you think back just now on the circuit, when you switch it off, okay, you're not going to have electricity, okay, because electrons are not moving through a complete circuit, right? Now the third one is the resistance. Okay, so resistance is actually the opposition of current flow, and you measure that in ohms. Okay, so for example, in this representation, imagine you have a couple of rocks here, okay, and when you have that rock, it's gonna get lodged in the pipe, you know, and the flow will decrease. So imagine from there to here. Okay, so you have the flow is going to decrease, okay, because due to the resistance. So whatever happens through the line here, if you think back about electricity, if along the way there is resistance, you're going to have much lower current than you expected. All right. So if we want to, so basically just now it's more, you know, in a small scale system. Okay, you have a circuit, you have a bulb, and you just want to turn that on and off. Okay, very easy. Okay, you zoom out a little bit, look at your house, right? So where does the power, okay, so in this case, if you have something like this, right, and you have your house here, okay, the energy requirement of your house, where does the power, where does the energy comes from? And we've discussed this about, you know, the power generation, power plants, okay, who actually generate the electricity for us. Okay? So if you think about that, actually electricity is a secondary energy source, right? Because, you know, if you think back at power plants, well, it's generated from something else. Okay? If you have hydropower, for example, it's generated from the potential gravitational energy, okay? And that is transformed into electricity through turbines and generators, right? And then you have it in the form of electricity. It goes through the transmission and distribution line, okay? And it reaches your house, and in your house, that electricity is going to be transformed into another form. Okay? So it depends. When you use kettle, okay, electric kettle, the electricity is transformed into heat. Okay. Whereas if you have fan, for example, the electricity is going to be transformed into mechanical energy, okay, because it's turning. So it's basically electricity is a form of energy transportation. right? So you have to think about where the power is generated from the power plants and how it gets to you in your house, right? And if you look at that, it's actually a very, very complex system, right? And we are going to look into that in, in just a moment, okay? But I just want to recap a few things here, okay? You have watt, okay? Watt refers to power, which is the rate of consumption of energy, okay? And kilowatt hour is a measure of how much energy one is using, okay? Not number of kilowatt per hour. Okay, I just want to highlight that because if you look at this one, for example, yeah, it's a very basic example. Okay, so if you have your light bulb rated at 100 watt, okay, if you to use 1 kilowatt hour of energy, it means you have to turn the light on for 10 hours. Okay, because it's rated at 100 watt. Okay, and that is the amount of energy that is used. Okay, so just keep that in mind, especially when you look at your electricity bill. Okay, it's always going to be in the form of kWh, right? Because that is actually the amount of what you use, right? So basically, that is with regards to what we use, right? So thinking back again to the power plants, right? How exactly that is generated, electricity is generated. So like I mentioned before, it's a complex system, but don't worry, we are going to look further into that, okay? So, but basically, we have to think back what we are using, okay? Imagine this is a house, all right? And actually it goes through a number of different systems, okay, from the source, which is the power plant, right? So if you think about that, right, basically, if you look very high up, okay, in terms of the country or the world, okay, the structure of our systems actually has many components, right? Of course, it has its own support components, and support here means, you know, you have different ways to measure and monitor the system. You have your protection system, but the main components are actually generation, transmission, distribution, and the load. Okay, and load here refers to the users, okay, the customers, you and me, you know, that is individual. You have your residential, you have commercial users, you have industrial users, okay, and the list goes on and on. But basically, this is how it is structured. So it's not only when we talk about electricity, of course, you know, we are always familiar with the availability of electricity. You just turn on your switch and you actually get the energy, okay, energy resource that you want. Okay, you can do whatever you want with it. But we have to think back, right? How actually the power plants generates this energy, okay? How it make its way to you, right? So it must undergo this. It first be generated, okay, in power plants, and then when this electricity is generated, it's going to be transported, okay, through a distance, okay, and that is where the transmission is, right? So when it is transmitted, when it is transported to a location, you know, a specific location, okay, and it reaches, it's near to the targeted users, okay, it's going to undergo distribution, right? So basically, distribution and transmission is quite similar in theory. Okay, the only difference is the voltage that is being transferred, okay, the phase, right, and also the frequency sometimes, right? So we have to, you have to remember, okay, in a power system, there's always going to be these three different components, okay, plus one, which is the load or the users, okay. So how electricity is actually generated at power plants, okay, because, you know, for the past few weeks, all the lectures, okay, we have been talking about generating power, okay, generating electricity. Okay, we've looked at the renewable and non-renewable resources. Okay, and it's always going to be something like you have a source, and then we do something with it where it produces a different form of energy. Okay, usually a lot of that uses turbine and a generator. Okay, and then after generator, it is you come up with electricity. Okay, that's the general way of electricity generation, right? But how exactly is electricity generated at power plants? In the generators, what actually happens, right? And to answer that question, okay, we are going to go back to basics again. Okay, so please bear with me. So basically, before we really look at how electricity is generated, we have to understand a little bit about current and magnetism. Okay, so if you have a normal magnet, okay, you have something like this, it has its own poles, north and south pole. So basically, in magnets, they have magnetic fields. Okay, and you know, the field, the direction always goes from north to south. Okay, but what if you have just a normal metal? Okay, if you have something like that, can you make it a magnet? Yeah. So, you know, it's a very interesting question. Okay, so basically, it is possible, right? So it is known that if you have for example, this is your metal, okay, and you put a coil over it where that is connected to a current, okay, and you have a constant flow of current in and current out through the coil, you are going to magnetize this metal, okay. So you have magnets, normal magnets, or you have a metal which is magnetized through the use of current. Okay, so basically, in the early 1800s, Joseph Henry and Michael Faraday are both credited with the discovery of electromagnetic induction. Okay, so that is the keyword there, electromagnetic induction. And we'll look into that further later on. Okay, so basically, if you, just now, I was talking about how you can magnetize metal, right? So Faraday, he has this thought, this idea, okay? So if we can magnetize something from electricity or from current, okay, is it possible to make it the other way around? So we have a magnet which can then generate current, because he just want to check that actually. So he devices an experimental setup, something like this, okay, where Now you have, so this is iron, okay? And you have the coil here. They have the power source, which is the battery. You have which will supply the current. Okay. When he did that, okay, what happened was that there was nothing happened. Okay, when it's static. Okay, but when the switch was moved, okay, so for example, switch it on, okay, and then this is connected, and suddenly he got a reading here, but it's very brief, just 1 second. Okay, so imagine, so instead of a galvanometer, if you have a light bulb here, okay, so when he turn the switch on, the light bulb just blink, okay, and produces light just for 1 second, and then it's gone. Okay, the light is gone. So he did that, and that happened. And when he switched it off, okay, the same thing happened, but the direction is different. So imagine before this, the galvanometer is moving here. When he switched it off, the galvanometer goes that way. Okay. So basically 1 second here and then another second here, right? But that only happens when the switch was turned on and off. So in between, the the current is 0. There's nothing. Okay. So he was very, very interested. Okay, because back then, the only source of electricity, the only source of current that you can have is a battery, and it only uses a chemical reaction. Okay, it's not an electrical sort of reaction. Okay, it's a chemical one. So after his study, so he concluded that a changing magnetic field induces an electromotive force. Okay, so what happened was that this is the right-hand rule, something like this here. I don't know if you still remember. So everything is at 90-degree angle. Okay, so you have your thumb here, which is the motion. Okay, so motion of the thing that is moving. Okay, and we'll apply that to that later on, but I just want to highlight here. Okay, the first finger here is the direction of the magnetic field, right? And the second finger is actually the direction of the induced current. Okay. So what happened was that something similar to what Faraday had done with this one, okay? But you have a coil here and you have the magnet. So when you move the magnet, okay, you have to think, look at the right-hand rule, right? But one thing that I have to highlight, okay, the movement, the thumb that shows the movement is not the magnet. Okay, it's the coil, because you have to look through what exactly the current is moving. Okay, in this situation, it's this one, right? It's the wire. It's not the magnet that we are testing. Okay, we're testing the wire. So if you move the magnet downwards, okay, so relatively the coil is moving upwards. So imagine you are moving the magnet, okay, but the coil itself, okay, is going upwards, right? So thumb is up, okay, and you have your direction, magnetic field, okay. So let's take a point here. Sorry. So let's take a point here, right? Because it's very different at different points of the coil. Okay. So if you have something here, sorry about that. Okay, then movement upwards for magnetic field. Okay, because the north is there, so you're gonna have something like that, Okay. Okay, you can do this with me actually, right? And you can then you will find out which way your current is moving. So in that situation, the current is moving there. Okay. And the direct opposite is true when you think about what's happening on the other side here. Okay, because basically it's moving upwards, yes, but the direction of magnetic field is actually like this. Okay, sorry, I don't know if you can see that, but you know, you can do this with me. So the direction is towards you, okay, the current. So you're going to have something like that. So now the current moves from here to the coil and then there, right? So that's when the magnet is moved downwards. But the opposite happens when the magnet is moved upwards. Okay, when it moves upwards, your coil relatively it's moving downwards. Okay, again something like that, moving downwards, and then your direction is like that. So your current is actually towards you. Okay, and there you have it. You have the flow of electron, okay, from here to here, okay, as the magnet is moving. All right. So basically, induced EMF. So basically, this is why it's called induction. So electromotive force induction, right? Because actually the electric is produced from the magnet. Okay, the magnetic field, changing of magnetic field, okay, and the angles and everything. So in law of induction, the induced EMF depends on the rate of change of magnetic field, the loop's area, and the angle. Okay, so this is just here, okay, but I do not expect you to memorize this or anything. Okay, just good if you can understand. All right. So in electric generator, okay, what is actually happening? Okay, you have to remember back what was happening just now with, you know, the right hand rule. Okay, how the magnetic field actually induces electricity. Okay, so the same thing happened in an electric generator. Okay, the basic description of generator is that it transforms mechanical energy into electrical energy. So I'm sure you guys know this already. Okay, that's what we've been saying from day one. Okay, it transforms mechanical energy into electrical energy. Okay, but how? Right? So if you look at this example, so actually this is an example of an AC generator. Okay, and in AC generator, you have your magnets here. Okay, you have your north and the south poles here, right? And you have actually a loop. Okay, so imagine this is a wire, right? So you have that loop which is connected to something which moves it. Okay, that's why remember why we have turbines. Okay? So turbines, hydro turbines, it moves like that, right? Which is the same if we look at wind turbines as well. Okay, it also moves like that. So that movement, that mechanical rotating movement, okay, is actually transferred to the generator. Okay, so imagine you have your so you have something here which actually turns it. So you have your, sorry, if you have your wind turbine, yeah. When wind turbine is rotating, okay, and that will rotate your coil here. Okay. So what happened is, imagine that the movement is, clockwise. Okay, it's clockwise. That coil will move, right? It's going to move something like that, clockwise motion. Okay, and you're going to have. Can you just bear with me 1 second? Okay. So if you have the setup, okay, I'm going to draw it in 2D here. Okay. Okay, sorry guys. Okay, another thing that is worth highlighting is you have slip rings here, graphite brush. Don't know if you can see that, it's there. Okay, and you have your basically the load here. Okay, so just imagine this generator is used to light the light bulb. All right, so when it turns, okay, it turns in clockwise motion, and you have your magnetic fields like this. Okay, that is the direction. Okay, so in that, when it's 180 like this, right? Okay, if you use again the right hand rule, you're going to find out that the current will move like this. Okay, so it's going to move in that direction. Okay, and that correlates with this part. Okay, up to here. Okay, it's going to move, it's going to generate the current, okay, as it turns, right? But then imagine that it comes to that point. So it's turning, okay, from 180 into a 90 degrees, okay, or rather 270, I would say. Okay, and in that situation, actually, if you think back here, if you look from this point onwards, okay, from here it's going to go down, right? But when it starts from this point, it's going to turn up, okay? And that will change according to your right hand rule, okay? And what happened is that you're going to generate the current in that side. So it's going to be opposite direction. Okay? So instead of the current moving like this, okay, it's going to move in, let me change the color, like that. Okay, so it's going to be from the opposite direction. Okay, and that is why we have this tool, basically, slip rings. Okay, so this is basically, if you think of this as an actual setup, okay, if you are going to, if you have your loop like that, okay, and that is then connected to your circuit. So you have your lamp here. Okay, right, you have your lamp there. Okay, if it's turning, okay, imagine what's going to happen to the wire here. It's going to get twisted, right? So that's why you have the slip rings. Okay, the slip rings will enable the turning of the coil without, twisting the wire. Okay, or whatever sort of connecting line that you have. All right. So Yeah, so that's what happened when it's a different direction. Okay, so that's why you have in AC. Okay, AC is actually alternating current, and that's what it means actually. So the current, it alternates from this direction to another direction, and it happens continuously as long as the motion is happening. Okay, when it stops, then of course no more current is being induced. Okay, and you're not going to get any more electricity. Okay, bear that in mind. Now, basically in electric generator, okay, remember just now we talked about what are the factors that affect the induction of EMF. So basically the same thing. The angle between static B and loop area, it keeps changing. Okay, therefore it induces the EMF in changing amount, okay, voltage, or what you can actually imagine from this setup. Right? Sorry about that. Okay, that is actually the how electric generator works. Okay, and how you can turn your mechanical energy, okay, from the turbines into electricity. Okay, which is then transported through the transmission line, and then goes to the distribution line, and finally goes into your houses. Okay, that's how. So I did mention it is a complex system, okay, but it's an efficient system, basically. All right. So I know we've been talking about AC generator. So DC generator is also similar. Okay, it uses basically the same mechanism, okay, except that it has split ring commutator instead of slip ring. Okay. So because it has a split ring, okay, I think you guys can Google this to get a more clear picture. But basically, because it has the gap here, okay, so as it turns, right, although actually the current, okay, technically it is produced in the opposite direction. However, because of the gap here, it makes the what is connected to here and here, okay, makes it so that it's only in one direction. Okay, that makes it confusing, but it's because this is more graphical. Okay, so you can actually go into Google and look it up. All right. Okay. Right. So this is actually a better representation. So you have just a comparison between the two types of generator. Okay. And I think this makes it more clear. All right. So this ensures that you can turn your loop without, without making any types of problems to the external circuit. Okay, so you have to look at that and think back. So this the slip ring is going to turn for AC generator. Okay, however, the brushes here is immobile. Okay, it's immobile, so it's in stationary. Okay, and it's going to brush the slip ring as it turns. Okay, and just remember, electricity, the requirement is that it must have contact all the time, right? That's why the brushes are there. Okay, it's what connects your circuit to your slip ring, right? And in DC generator, okay, this is what happens. So as it turns, right, the brush is here, Okay, so imagine when it comes to this gap, right? It's going to change into this side. Okay, and that is actually, it's designed in such a way that this change in phases, or from this plate to that plate, it coincides with the alternating direction, okay, that's happening here. So basically in this portion, it's similar. The only difference is here. Okay. So if you think about that was generator. Okay, so generator, it generates electricity. Okay, and just to throw it out there, electric motor is actually the very opposite. So it uses electricity to generate mechanical power. Okay, so now we look at transmission line. Okay, because you have the power generated. Okay, but how does it go from the power plants to your home? So imagine it involves large distances. Okay, and as you transport that amount of power across large distances, power loss is unavoidable. You cannot avoid that because there's always going to be some energy lost to the environment in the form of heat. Okay. However, this loss can be minimized if the power is transmitted at high voltage. Okay. So you have, if you look back at this equation, okay, P equals to IV. So power is equals to current times voltage. Okay. So power is constant. Okay, it's the same amount of power, same amount of energy. However, if you transmit it at a high voltage, okay, automatically the current is lowered. All right. So this, how do we increase, okay, or reduce the voltage, right? So if you look at the normal way of transporting the electricity from the power plant to your home, you're going to have something like this, okay, the power plant, okay, and then it goes to step-up transformer. Okay, so step-up, I think you can already relate to that. So that is actually where the voltage is increased, okay, and it goes to the transmission line. So imagine as this one here, because usually transmission line is long. It's a very big distance. It's not 1 kilometer, it's not 10 kilometers, can be hundreds of thousands of kilometers, right? So you have a high voltage transmission line, okay? And when it gets to basically the area where the energy is to be supplied, okay, it's going to go through step-down transformer, okay, where the voltage is lowered, okay, and then it goes through the distribution line. So this is transmission, but here is a distribution. This is what you see, you can normally see. Okay, you have your you have your power lines there, even in front of your house. Usually, okay, you have something like that, and that goes to your home, right? So transformer is not this one, okay? Although, in terms of movie, I guess Transformers is quite an entertaining movie, right? But transformer in this situation is actually a device used for increasing or decreasing an AC current through step up or step down of the voltage. So this is an example of a transformer. Transformers consist of three main pieces. You have your core, okay? This one is your core. So, and then you have two individual sets of wire coils. You have your primary okay, primary coil, and you have your secondary coil, right? So how transformers do the step up or step down? How does it increase or decrease the voltage? That is done simply by adjusting the ratio of coils on one side to the other. So imagine when you want to step it up, okay, you have 5 coil here and you have 10 coil here, okay? So it's going to step it double, all right? So transformers actually, they only work if the current is changing, okay, which is why electricity is usually transmitted as AC, okay, alternating current. All right. So if we look at the basics, okay, what's happening normally in power systems. Now we will look a bit more what's happening in Malaysia. Okay, so in Malaysia, actually, we have many players, okay, not only TNB. All right, so power industry players in Malaysia, the biggest one, of course, is Tenaga Nasional Berhad, TNB. And then we have in Sabah and Sarawak, we have Sabah Electricity Sdn Berhad, SESB, which is 83% is owned by TNB. And then we have Sarawak Energy Berhad, SEB, okay, which is under the purview of the Sarawak government. So basically, the business, the power business in Malaysia, so we have 25,000 megawatt of capacity, and that comes from different generation mix. Okay, we have oil and distillate, solar, hydro, gas and LNG, and also coal. Okay, although the majority now is coal, and this is the latest figures from 2020. Okay, but if you look here, generation market share of TNB is actually only 61%, 61.5. Okay, there's actually other players, right? So generation is actually one of the essential components of our system, as we've looked before, okay, about how energy is generated at power plants. Okay, so power plant is designed to generate electricity from another energy source. Okay, and you can look back at conventional and non-conventional energy. Okay. So usually they generate voltages at 11 to 20 kilovolts and frequency of 50 or 60 hertz. Okay, and then you have your large substation, which is used to step up the voltage. Okay, and other substation at the other end to step down the voltage. Okay, it depends on how what are the demands and what are the consumers at the other end. Right. So basically, main power producer in Malaysia, we have TNB, okay, SESB, and SESCO. SESCO is Sabah, okay, and SESB is Sarawak. We also have IPP. Okay, IPP is actually independent power producer. And then we also have co-generators. We'll look into that after this. So independent power producer, IPP, is actually power producers which are privately owned. Okay, it's not under TNB. Okay. However, they have a long-term agreement with TNB in which IPP sells power. So they generate their own electricity, okay, and they sell that to TNB, okay, through an agreement. So this generated power is connected to the national grid. So we look for the international grid in a few more minutes. Okay, so keep that in mind. So basically, a few examples of IPP is Akbar. Okay, it's owned by YTL Generation. Malakov Berhad, which owns Lumut Power Station, Prai Power Station, and Tanjung Bin Power Station. And we also have Genting, okay, which owns Kuala Langat Power Station. Okay, so remember TNB is not the only player in the power industry, especially in the generation. Okay, of course, in transmission and distribution, that infrastructure is developed by TNB. But otherwise, where the money is in the generation. Okay, and there are other power producers at play. Right? So apart from IPP, we do have co-generators, and co-generators are minor electricity supplier. Okay, and it happens that some small distributors, they buy electricity from the utilities, okay, or they also generate their own power, mostly by co-generation. They then distribute this power to customers within specific areas such as industrial complexes. Okay, so some examples of that is Petronas Gas, which generates electricity as a co-generator and distributes power within 2 integrated petrochemical complexes in Gebeng and Kerteh. Sorry about the typo there. KKIP Power, so they purchases power from SESB and distributes that within Kota Kinabalu Industrial Park, right? So that is co-generator. Right, so we have generation, okay? That is one part. We also have transmission, okay? I know I've gone through this a little bit just now, okay? When we are talking about how the generators in power plants work, but basically transmission is infrastructure that allows electricity to be transported over long distances. Okay. So basically, this is similar to what I have already explained before. So you guys are welcome to read this, pause this and read it if you'd like. Okay. However, what I want to highlight here is the national grid. Okay, so national grid is what we have in Malaysia, although in other countries they have their own version of grid, right? So what exactly is power grid? Okay, imagine you have, again, I'm using the same concept, and this is the basic one. So you have your power plants, which is generating the power, and then you transport that over distances through transmission, okay, and then distribute that to the consumers. Okay, you have that, and it used to be that one area is supplied by one power plant, right? So what happens if you look at the country as a whole? Okay, is it possible to have just one power plant to produce energy for the whole country? Okay, is it possible to have just one here? Right? Not possible. So even now we have, I can't remember the exact number, okay, but we do have a lot of different power plants across the country, not only in Peninsula, but also in Sabah and Sarawak. Okay. And another thing, okay, when you look at the load profile, okay, load profile here means the energy requirements. Okay. So in a normal day, 24 hours, you're not going to have a constant energy demand. Okay, and there's so many things, there's so many factors that affect how much power is required. Okay, and imagine that this is at one place, for example. What about the whole country? What's going to happen in Kuala Lumpur? Is it similar to what's happening in Kuala Terengganu? No. Okay, so this variation, this variability in load profile, it introduced more complex situation in terms of power. Okay, we're going to need a system where we can generate power effectively, can generate electricity effectively, okay, being mindful of what is produced what it comes from, energy resources, okay, and where the demand is and how that demand changes. So it's a very dynamic situation, okay, and that is why the grid system is something of an innovation. It's a very big innovation. So basically, the grid system is a system of generation, transmission, and distribution of electricity, covering larger network across countries or even continents. Okay? So the grid system ensures a continuous availability of sufficient energy supply for all consumers. Okay? And you actually have an adequate margin between supply and demand. So you're not going to produce only enough, because sometimes what happens if one power plant shuts down? Okay, you're going to have problem in terms of blackouts, right? You're not going to be able to meet the supply. So the grid system also develops and maintains efficient, coordinated, and economical transmission system for bulk delivery of electrical energy, right? So the national grid is our version of our grid, okay? And of course, the objective is to ensure a steady supply of electricity to consumers, operators of the electric power system, okay? They call on electric power plants to produce and place the right amount of electricity in the grid at every moment. And this is a very dynamic situation. Instant demand, okay, sudden demand must be instantaneously met and be balanced. Okay, that is the challenge. And with the existence of the national grid, power plants do not generate electricity at their full capacities at every hour of the day, right? So you don't have to maximize the use, you can optimize it instead, right? So there are three major types of generating units. You have base load generating units, okay? And this actually supplies all or part of the minimum or base load on the electric power grid. Okay? And the base load usually runs continuously. Okay? They produce electricity at nearly constant rate throughout the day. And then you have your peak load. Okay, so usually, for example, in the morning versus night, okay, the demand is going to be different because, in terms of what you use at your house, okay, the habit makes it different. So that is only in terms of residential, but what happens at commercial and industrial level, which basically are users of bigger proportion, right? So when you have peak situation, so peak load generating units, they help to meet electricity demand when demand is at its highest, such as in the late afternoon or when electricity used for air conditioning and heating increases during hot weather and cold weather. Okay, so they're relatively inefficient and very costly, but they provide, the high value service during these times of need, okay, during peak times. And then you have your intermediate load generating units, which is actually the largest generating sector. They provide load responsive operation between base load and peaking service. So anything in between is supplied by intermediate load generating units, right? So basically the advantage of the national grid, so instead of having a localized supply of energy, okay, you have a centralized system, and this centralized system allows various power plants and producers to share infrastructure for transmission and distribution, which led to increased reliability and lower costs. So in terms of reliability, it's more reliable because you have this interconnection and you have multiple routes for power to flow. And you can allow various generators to supply electricity to many load centers. Okay? It doesn't necessarily mean you have a specific one generator for one place. Okay? You can actually make use of different ones across the country. Right? And then the economic benefits is, or you can operate larger units to serve combined electricity demand at the lowest possible cost. Right? And lastly, the stability of the electricity grid requires the electric supply constantly meet electricity demand. Okay, and this requires coordination of various entities that operate different components of the grid. So we have the national grid, but actually recently, okay, we are also going towards powering ASEAN. Okay, so they call it ASEAN Power Grid. So for example, the national grid is actually interconnected to Thailand's transmission system operated by Electricity Generating Authority of Thailand in the north via a HVDC interconnection with a transmission capacity of 300 megawatts and a 132 kilovolt HVAC overhead line with maximum transmission capacity of 80 megawatts. Okay. And not only with Thailand, we have also connection with Singapore's transmission system at Senoko in the south via two 230 kilovolt submarine cables with a firm transmission capacity of 200 megawatts. Right? So it's something where, not only in the country, but we can actually coordinate within ASEAN, all right, to share and coordinate our power system. So the future of our grid, of course, with the advance of IR 4.0 and the Internet of Things, we can make use of that actually, okay, to make a smart grid. So we can have real-time data, and through the use of AI, we are able to make it even more efficient, okay, and more convenient. Right? So that is for, in terms of the country and ASEAN. Okay? But looking back to our own usage, okay, actually, we have to look at our electricity tariff. Okay? And if you look at your electricity bill, okay, you are charged according to how much electricity consumed. Okay? And that actually depends on the type of activities at the premises. So it's the rates are different whether you are a residential, commercial, or industrial customer. But basically, the objectives of tariff is, the production of energy requires cost. Okay? So people, investors, need to recover back that cost. So it includes production costs, capital investment, okay, operation and maintenance costs, and of course for profit. Okay. So if you look at your bill, ask yourself, what does your energy bill tells you? Okay, and how do you know it's correct? And lastly, how can bills be used to target and monitor change? Okay. Those are the questions. So basically, in terms of bills, we have to look at, so number 7 here is actually what type of customer you are. Okay, in this case, kediaman is residential. So that will tell you what are the tariff, okay, that is applicable. And then, of course, number 9 is how much energy that you use actually. Okay, that is in kWh. Okay, remember earlier on, we've already differentiated what is watt and what is kWh, kilowatt hour. Right, so that is the use that is your electrical usage, okay, for that month, for example, or for this billing period, right? So we will look into, okay, change in lecture 8, right? Because that is more appropriate for that discussion. Right? So basically, when you look at tariff, just know that the different rates are available for different types of customers. So you have commercial tariff, you have industrial tariff, okay, mining tariff, and also specific agriculture tariff, apart from the normal residential tariff. Okay. There's also some others which you can also look at in PNB website, right? So before we finish, just one last slide on energy a Malaysian perspective. Okay. So if we talk about energy in terms of producers and for us as the customers, okay, basically there are various stakeholders, like the industry, have people like us, the residents, okay, have people in the commercial sectors, have the government, right? And we need to look at energy efficient technologies and processes, okay, to make sure that you can consume less energy, but with the same productivity, right? And in terms for us, access to electricity, that is very important. And then we have our own choice to use appliances that has a more energy efficient rating. Okay? And in commercial sectors, a lot of talk has been done on energy efficient buildings. Okay, how you can save energy and at the same time reduce environmental effects. So that includes your carbon footprints and various green practices. Okay. And lastly, in terms of the government, okay, the government is very highlight the importance of energy security, okay, and to cut down the energy expenditure. How are you going to do that? Okay, so it's interrelated. Okay, it fits from one to the other. Okay, and it links very intricately the economy through our social and also through the environment. Okay, and we will look further into that in our next lecture, which will cover the socio-economic of energy, right? And with that, I thank you, right? If you have any question, please contact me through WhatsApp, email. Thank you very much for your kind attention and bye. See you in the next lecture.